Hello everyone, welcome to this talk on understanding the transformer, a breakthrough in NLP. In this talk, we will start with a brief history in NLP, and then we'll see why did we need the transformer architecture, and then once we start learning about the transformer, we'll break it apart into various components and understand why it works so well. And finally, we will see a beautiful application of this architecture called BERT. Let us start with a brief introduction about myself. My name is Varun. I'm currently a third-yearite at IIT Guwahati. I'm selected for summer internships at Amazon and Adobe research teams. I've also done a couple of research internships. One of my research internships involved working in the domain of NLP and transformers. I've learned a lot about transformer architectures, which helped me understand the architecture and the transformer concepts very well. So let us start without any ado. NLP is a very old knowledge and subject. One of the basic sequence modeling approaches that were introduced in NLP was bag of words model. The bag of words model involved building a complete dictionary of the words that were present in our text. This dictionary was then used to one-hot encode every word in the sequence. This process was highly inefficient because of the space and time complexities. It also did not encode the sequence information from the sentences. In order to solve some of these drawbacks, recurrent neural networks called RNNs were introduced. Let us see what were. Recurrent neural networks, which can also be called recursive form of neural networks, learn a function with sequential inputs. A time step is taken by each RNN cell. The box here represents an RNN cell. A time step is taken by it, and a part of the hidden state is output, and the context is passed to the next time step. We can better understand the concept of RNN by unrolling it. This is an unrolled version of RNN network. Every step involves taking the time step sequence input, outputting the hidden state, and then passing it as a context to the next time step. If we zoom into the internal working of RNN cell, this will look something like this. The time step and the hidden state context are concatenated and the tan-edge activation is applied. This nonlinear function helps efficient learning of the contextual information. However, this RNN had some drawbacks associated with it. Let us see what were. The major drawback in RNN were vanishing and exploding gradients. To understand this drawback, let us assume a function for the RNN cell. If A is a function for each RNN cell, it will be taking two inputs, the hidden state and the time step input. Both of them, if we plug into the activation or the RNN cell function, this will give us the next hidden state. Since this is a recursive function, we can write the function in this form. This will give us an equation for the H, hidden state at third out. If we assume a more specific function for the RNN cell, then A of H comma X, we can write it as Wx plus ZH. For analysis, we can simplify our analysis right now by ignoring the activation function for now. The activation function tan H is ignored in order to understand the working of powers better. If we plug this expression into this equation, we arrive at this equation. The hidden state at nth time step equals the weight part raised to n times. This is where the drawback comes. This weight parameter is a learnable parameter. This is learned by the RNN by doing forward passes and backpropagation. During backpropagation, the gradient is also raised to the same power as a weight. Now, imagine the gradient is small. It is say 0.5. If you raise 0.5 to a power of n, now what is n here? N here is the length of the sequence. In text and usually in NLP, the length of the text is large. For example, you can have a 5 into length text or a 256 length text. If you raise a small number to a very large power, the output will be very small. This will lead to a very low gradient. This problem is called vanishing gradient. This does not allow the RNN to learn fast and better. Now imagine the gradient is a little above 1. Now if you raise such a number to very high power, the gradient becomes very huge and we'll end up with NAN losses. This is not really expected while training. This is called exploding gradients problem. This vanishing and exploding gradients does not allow us to efficiently train the RNN neural networks. Another drawback with RNN was a single context passage. Since for every time step, we pass a single time step context and we do not filter the context at all, this does not lead to efficient transformation of the context. This does not learn the context represented by the sentence better. In order to solve some of these drawbacks, a new kind of network called long short-term memory networks were introduced. These are termed as LSTMs for short. Let us look at how exactly LSTM looks. This is a detailed version of LSTM. You can see LSTM is a complicated version of RNN. It has an extensive structure inside it in order to transform the context better. It consists of various gates called input gates, forget gate, and an update gate. These gates determine how much of the context to retain in the specific time step and how much of the context to pass through to the next time step. As you can see, it consists of two context passages. LSTMs were extremely capable of learning the sentence information good. However, LSTMs also pose certain drawbacks. And this led us to exploring different neural networks in order to represent text better. Then arose the need for transformers. Why did we need transformers when we had LSTMs? What were the drawbacks with LSTMs? One of the drawbacks was a huge number of parameters. As you saw in LSTM, it consists of a lot of gates and activation and concatenations. These gates involved a lot of parameters. Now this was just one time step. What if you had many time steps? The number of parameters introduced a lot. The large number of parameters make the LSTMs take longer to train and make large gradient paths. They also demand a very fine-tuned weight initialization techniques for efficient learning. Also, one of the drawbacks was that transfer learning was not possible in LSTMs. Transfer learning was very popular in computer vision domain. It involved us to use weight initialization from the models that were trained on large data sets. And since transfer learning was not possible, LSTM models required a lot of data sets as we could not fine-tune on the previously trained weights. Now this led us to the invention of the transformers. So now let us start the main topic that we all came for, the transformers. This is a representation of the transformer. The image is taken from the paper itself. The paper Attention is All You Need, which first introduced the transformers to the world. On a first glance, you can see the transformer is divided into two parts. The first part that is called an encoder and the second part that is called a decoder. The basic components of both encoder and decoder look quite similar. For example, the feed-forward networks, the attention, the multi-head attention to be specific, the add and norm, and also you can see the input embedding, you can see positional encoding. All of these terms might seem very intuitive, but at the end of the presentation, this will look very easy. You can also notice some skip connections, which you might already know. There are residual connections, which allow us to make the model more and more deeper. Let us look at things specifically. If we zoom into the transformer architecture, we can see something like this. We can see the self-attention, we can see the layer norm, feed forward, and the layer norm. The embedding of the input is added to the positional encoding. The position encoding is a new concept that was introduced. We'll learn more about in the later presentation. Both of them are added and then passed to the self-attention. The self-attention is used in both encoder and decoder, and a modified form of self-attention called encoder-decoder attention is used while transferring information from encoder to the decoder. If all these seems complicated to you, hold on. We'll be learning more about self-attention. What is self-attention? Why exactly do we need it? Self-attention is a concept which allows the model to learn which part of the sentence affects which part of the sentence. For example, this is a sentence that you input to the transformer. The horse could not run in the race because it was too tired. Now the word it might refer to the race or the horse. How do you expect the model to learn it? This is made possible by self-attention. The self-attention learns the representation of each word by combining the inputs, by combining the information from other parts of the sentences. This is called attention. The transformer teaches the words to pay attention to its surroundings and all the words. This was a brief walkthrough of self-attention. Let us see in specific, how does transformer exactly go about attending the words? For example, you have two words, thinking and machines. You have embedded these words into vectors. We'll understand more about how this embedding is created in the later part of the presentation. But for now, let us assume that for every word, we have an embedding available. This embedding is of fixed size, and then this embedding is used to generate subvectors called queries, keys, and values. These queries are generated by multiplying the embedding to the weight matrices. The query weight matrix is multiplied by the embedding to get the query subvector. Similarly, the key weight is multiplied to each embedding to get each key vector. The value weight is multiplied to each embedding to get each value vector. Now, what does the transformer do with all these queries, keys, and values? It basically uses these queries and keys to understand the importance of other words to the other words. Let's see the next step. Now, imagine you need to create a new representation for the word thinking, while also incorporating the knowledge from the other words. For that, you need to learn how much the other words affect this word, right? Hence, use a query of the word that you are creating the representation for and multiply it with the keys for all the other words. For example, you're creating the embedding for thinking here. You take the query of thinking and multiply it with the key of thinking and machines and all the other words that are present in the sentence. In this way, you create a score. This score represents the amount of attention that is given to each word. Now, generally it is expected that while creating the representation of the word, most attention will be focused on the word itself and also on some of its neighbors and some of the other words as well. Hence, you generally expect the score of the self word to be high. The multiplication is a dot product which is performed between these two vectors. Now, what is the next step? Next step is to divide by the root of the length of the embedding. The length of the embedding of the queries and keys is fixed to be 64 by the original paper where this was first introduced. And then it is divided by the 8, hence the number 8. This division allows efficient gradient flow and also sets the time complexity of the attention to a fixed value. After dividing by 8, you softmax these values in order to make them sum to 1. This tells us how much of the attention is focused on which word. So while creating the representation of the word thinking, 88% of the attention is focused on the word thinking and 12% of the attention is focused on machines. So hence, the information from machines will be helpful in understanding the word thinking. This is the primary concept that is used in self-attention. Now, what is done after softmax? After softmaxing, we multiply the word with the value, the corresponding values. So once we have multiplied the values, we sum all of them to get the final representation of the word thinking. So Z1 is a new representation of the thinking. Now this Z1 also contains information from the word machines. Now how does this information come through? You multiplied it with the value, the word machines. This value was created from the embedding of the machines itself. Hence, this allowed an information flow into the final representation. This was single self-attention. But if the transformer sits down and performs this calculation over and over again for every word, this will be highly inefficient. Transformers, deep learning in general, demand vectorization. Vectorization and matrix calculations help in faster calculation and allow the models to be trained on bigger computers like GPUs and TPUs. All the steps that we discussed earlier can be performed in 2 steps with matrix calculations. Imagine these are the 2 embeddings of the word thinking and machines. We can concatenate both of them and multiply with the query matrix at one time to generate all the queries. Then again, with a single step, we can multiply with the query matrix, the key matrix to generate all the keys. In this way, we have generated all the query keys and weights in one step. In the next step, we can perform all the remaining steps using this mathematical formula. We multiply query by keys, divide by the root of the embedding length, we perform the softmaxing, and then multiply with the values to get the final representation of all the words. This fast calculation heavily simplifies and made the calculation of the attention of the transformer very fast. This matrix multiplication and all the steps that we saw earlier was a single self-attention. Another new concept that was introduced by transformers was the multi-head attention. Now, what is multi-head attention? You have the embeddings, you generate attention vectors multiple times. You generate multiple sets of query keys and values and combine them all at once. You did not understand? Let us do a better representation. You perform the query key and value and all the steps that we talked about earlier to get the attention vector Z0. You then use another set of query keys and values to generate another representation. You again use another set to get another representation. In this way, we use multiple attention heads in order to get multiple representations. Once we have all the representations Z0 to Z7, we concatenate all of them and again use a learned weight parameter to get the final representation. Now, how does this help? If single head attention is a beast, imagine multi-head attention as a multi-headed beast. It performs much better. Let us see an example where it can perform better. This is a sentence which is very similar to the sentence we first saw. The animal didn't cross the street because it was too tired. Now here, the word it can focus on the street or the animal. The orange color represents a head of the attention, and the green color also represents the another head of the attention. You can see one head of the attention focuses on the animal, and another head of the attention focuses on the street. In this way, different heads of attention focus on different parts of the sentence, and also different attention heads modify the vectors and generate different pairs of query keys and values. This allows the model to understand the sentence in a better manner and learn the sentence better. Let us see this image of the zoomed in transformer again. Now that you understand self-attention, this image might look a bit easy for you. You have the embedding, you do self-attention, you then pass it to the layer normalization, and then feed forward it, and then you go to the encoder. If you zoom it even more, you'll see something like this. You have the embeddings for every sequence, you generate values, keys, and queries, and perform self-attention. After many layers of encoder, you get a final encoder output. And the decoder, for the encoder and decoder attention, you generate values and keys using this encoder output, but you generate query using the decoder output. This is called encoder-decoder attention. The self-attention is done at the bottom of this decoder, and encoder-decoder attention is done at the top. Now let us see what is this position encoder. In the LSTMs and RNNs, we saw that they are the functions to represent a sequential input. But in the transformer, we pass all the sentences, all the words in the sentences at once. This does not allow transformer to learn the positions of the word. To solve this problem, where to represent the multiple words in the sequence as a sequential input, attention is all you need. The paper represents positional encoding. This positional encoding is a very useful concept that allows the transformer to learn which word is present in what part of the sentence. They use sine and cosine waves to teach the transformer about the positions of the word. Imagine, for every word, you create embeddings. Along with embeddings, you also create position encoding. You add both of them to get the final embeddings, which you then pass through the self-attention. Now, how exactly do you create position encoding? You create position encoding by using sine and cosine functions. You calculate the sine function and calculate the cosine function and place them, concatenate them together. This is a representation of the positional encoding. Now, you can see the positional encoding of the position. The pause represents the time step of the word in the sequence. And I represents the index of the embedding. With both of these, we can calculate the positional encoding as pause comma 2i, the sine of pause by 10,000 power 2i by dimension of the model. After calculating the sine embedding and cosine embeddings, we can concatenate them together. For example, let us see this example. This is an embedding with embedding length 4. And the time step of this is 0. So if we input it into this equation, we get a 0 value because position 0, right? We get the position encoding 0. And for this, we get cos of 0 as 1. So the first two indexes will have the zeros and second two indexes will have 1. You can see that is the positional encoding. You add these positional encodings to the token embedding to get the final embeddings of the word, the token. This is the final tokens that are passed into the transformer for learning. The attention is all you need authors also used a learned form of positional encoding, but it gave almost the same result. Hence, they finally fixed on these positional encodings. This is one way to encode the positional encodings. Another way which the original authors recommend is to interleave both of the positional encodings. The token position and the embedding dimensions are interleaved. The sine and cosine of both of them is interleaved in order to understand the position. These are the embeddings and this is a sequence. Now that you understand the basic concepts in the transformer, let's put them together in order to see what exactly is the transformer doing. You have the positional encoded embeddings, which you pass to the self-attention. Another copy of this positionally encoded embeddings are given as a skip connection to the add and normalize layer. The self-attended representation and the original representation are added together and normalized. These skip residual connections help us to build the model go deeper without worrying about vanishing and exploding gradients. The residual connections are very famous in computer vision domain as ResNet models. They have a lot of success and represent the image as well. And they were inspired to use the residual connections in order to build the model deeper and deeper. You can see the skip connections are given everywhere in order to learn the identity function. You can learn more about the skip connections and why it was used in the original ResNet paper, in which they beautifully explain everything about why do we need the residual connections. The output of the add and normalize layer is then given to feed forward, and then it's add and normalized again. This is a single encoder. Similarly, you can have another encoder layer, and you can stack many encoders on top of each other. After coming out of multiple encoders, the embedding is then passed to the decoder. The decoder also has a sentence which is performed, which is attended on, and then added normalized, and then this decoder output along with this encoder output together go into encoder decoder attention. The encoder decoder attention, as we saw earlier, is a special type of multi-head attention where the encoder embeddings are used to generate the queries and keys, and the decoder embeddings are used to generate the values. And together they perform the encoder decoder attention and again go into an add and normalize layer, followed by feed forward and finally add and normalize. And this is a one decoder. The same embeddings are given to another decoder layer. After passing through all these encoders, the output is given to a linear layer and finally a softmax layer. The softmax then decides which token to output. This outputting of single token at a time is called an auto-recursive model, where you give this part of the sentence and then expect the decoder to output the next token is called auto-recursive models. Now, this was a single transformer that you saw. Some of the Google scientists explored and introduced BERT. A BERT is a transformer encoder architecture. BERT is an acronym for bidirectional encoder representations from transformer. It presents two models, basically, the BERT base and the BERT large. The BERT base models involves 12 layers of encoder and 12 layers of attention heads, where you stack each encoder on top of them. You take a sentence and pass it to the 12 layers of encoder to generate the final embeddings. This encoder architecture, this BERT is trained on a large text dataset, usually on book corpus and Wikipedia text dataset, in order to learn the representation of sentences better. BERT is also used for transfer learning a lot. Whenever we need a new dataset, we just initialize a BERT and initialize the weights that were trained on large text datasets. This allows an efficient transfer learning based approach, which is very helpful today. The BERT large has 24 layers with 16 attention heads. Now, a lot of pictures and information were taken from various articles and YouTube videos. The links of all of them are appended here. The Attention is All You Need paper is a must go through if you want to understand more about the transformer architecture. There's also a YouTube video explaining the history before transformers, that is RNN and LSTMs better. This Jalmer.gitoto.io blog is a very helpful one as well. And all these more blogs help explain the transformer architectures very well. I really encourage you to go through them. Thanks for this. If you have any questions, you can write to me at my email or social media. Thank you.